So here we are on problem 3 on the midterm, and we're looking at part A. So this question is slightly tricky in the sense that you can't immediately tell whether the answer is true or false just by looking at the question. So you have to work your way through the question and try to see if you can reach a simple form or something very obvious from where we can easily deduce whether it's true or false. So the best way to attack this problem is to draw pictures. But before that, we'll try to see what the question is exactly asking. So you know there are two events, A and B, and the probability of A is less than the probability of B. Of course, we have natural bounds of 0 and 1 on the two probabilities. And now we want to find out that if we have some information about B, or if we know that B happens, does that tell us anything about A? Or can A suddenly have more probability than it had before? So how do we go about this question? Let's try to draw a picture, right? First, let's draw the universal set, or this is the sample space of all events. And let's draw A, let's draw B. That's A, that's B. So once you know that B happens, right? Once you know that B happens, what do you know about A happening? So now A can only take these values, because once you know that B happens, then you're enclosed within this circle here. And now you know that if A has to happen after B happens, then A has to lie within that interval. So when you look at this, you try to see, well, maybe I can construct an example where if I know something about B, I know a lot about A. Is that possible? Well, let's look at another case. What about this? So now if we know that B happens, do we know anything about A? Well, we know that A and B are mutually exclusive. So, well, probability of A happening slightly, now probability of A happening now becomes 0, right? Because now we know that if B happens, A cannot happen. So this is obviously not a counterexample, because now probability of A, when it was previously non-zero, now it goes to 0, right? Here we can't really tell. In example number 1, we can't tell. In example number 2, we know that it goes to 0. Now we've seen that they intersect when we saw the example where they intersect a little, you can't say much. When they don't intersect at all, we saw that we can actually conclusively say that the probability of A given B goes to 0. Now let's look at another example. What about when when A is completely contained in B, right? So that's the only example we have left. It's part of the intersection example, but it's slightly different. And what I'm going to do now is I'm going to draw A and B in boxes so that it's easy to see why or what happens. So let this be B and let this be A. So A is completely contained within B. So this is the boundary for B. Let's actually make that a little dark. Let's remove the last one and do that again. So now what do we see? We see that once we've been given that B happens, then we are going to be somewhere inside that box, this big box right here. And outside this box, if we don't know anything about B, we see that probability of A is just the probability of landing in this box of the size of A. And since the box the size of A is much smaller than the box the size of B, or not much smaller, slightly smaller than the size of B, we know the probability of A is less than probability of B. But now, if we know that we have landed in the box B, you can see just by the area of the two boxes, since A is almost the area of B, once you know that you've landed inside B, chances are that you've landed inside A, because A fills up most of B. So the counterexample, as we're seeing here, is now that you know that B happens, you have a much larger chance that A happens, because you know that if B happens, almost always A happens, right? Because now once you've fallen inside here, the only way A cannot happen is if you end up falling in one of these spaces here. So when I say falling, what I mean is that you have an event, and whenever event A happens, B always happens, as in A is completely encompassed within B. So what I mean by falling is that when you see that some event happens, it happens to be of type A or type B. That's what I mean by falling, right? So now we know that once event B happens, there's a big chance of event A happening. So the probability of A occurring, given that probability of B occurring, now shoots up, right? So this is the intuitive understanding behind drawing a diagram first. So we see the probability of A given B might shoot up, right? So now that I've given you some sort of an intuitive understanding of why this might be a counterexample, let's actually look at a particular case where this is potentially a counterexample. Let's look at a 6-sided die. Let's say B event that 1, 2, 3 one of these spelling, right, that one of these three occur. Let A be the event that 1 or 2 occur. So you know that when A happens, B definitely happens. I'm going to actually put this 1 off occurs, 1 off occurs. So let B be the event that either one of or one of 1, 2 or 3 occur when you roll a 6-sided die, and A be the event that 1 or 2 occurs. So what's the probability of A? Which is equal to 1 over 3, right? You have 6 different options, and if you have 1 or 2, which is 1/3 of all the options, then you have, I'm just going to say fair. So and you have that when 1/3 of the option possibilities occur, then A occurs. So therefore the probability of A is 1/3, which is less than the probability of B, which is half, because 1, 2 and 3 consist of half the sample space, and since every single point is equally likely, and B has half chance of occurring. But now once we've been given that B occurs, what's the probability of A? Right. So once we've been given that B occurs, then we know that the die came up as either 1 or 2 or 3, and you know that A occurs when either 1 or 2 occurs. So out of the 3 options, 2 of the options means that A occurs. So now we know that the probability of A given B is 2 over 3, because once you know that B occurs, or that the die came up 1, 2 or 3, the probability of A occurring goes up a lot, because now you know a lot more, or the amount of space you have to work with has shrunk around A. So you have a much larger chance of A occurring than you did before, because now you know that, well, A is most probably going to occur because B tells me a lot about A. Therefore, this is greater than 1 over 2, which is equal to P of B. Therefore the answer is false. And we've constructed a counterexample only when B tells you a lot about A. And I wanted to briefly talk about the mistakes people made in this question. Sometimes people came up with almost a valid counterexample, but then they came up with a counterexample in which P of A intersection B was greater than P of A or P of B. This is not possible, because the intersection of A and B has to be it can only be as big as A or B. It can't be bigger than them, because the intersection of two things is the points where both of them happen. So the intersection of A and B cannot be a bigger set than A or B. Therefore, if P of A intersection B is greater than P of A or greater than B, then you know that you're making a mistake. And sometimes people just came up with a counterexample where P of B happened to be smaller than P of A, which the question was not asking for. And sometimes people assumed that P of A, I'm just going to put these off, P of A given B is 1. This can't happen, because you can't have complete knowledge of A if you know that B happens, right? Because if you have complete knowledge of A when B happens, that means B is contained within A. That means when B happens, then B is one of the events which forces A to happen. But if that's the case, then probability of A should be at least as much as probability of B, right? But that's not possible because the question demands that the probability of A is less than probability of B. So these two are the main common mistakes which people made on this question, and I just wanted to point those out. Alright, so that's it for problem B, problem A, part A of problem 3.